Cyclothems. This is the whole idea of cycles. We already talked about how the rocks have this repetitive pattern. We have limestone, mudstone, limestone, mudstone, limestone, mudstone kind of thing. This is repeated literally dozens of times. From what we've already said, the limestones represent marine conditions of various kinds. Sometimes shallow marine, sometimes a little bit deeper, sometimes intertidal, but marine, ocean water. These are, for the most part, with some exceptions, for the most part, they are fossil soils. If you go study them, they have the same kinds of features, the same kind of structures that you find in modern soils. You can actually classify them in modern soil taxonomies by looking at their structures. Different soils form in different climates and different environments. So if you were here, or if you were in southeast United States, or if you were out west, or if you're up north, the soils would be different for a variety of reasons. And climate is one of those. So you get different types of soils formed, and they have different general characteristics. Okay, and we can, some of those, not all, but some of those characteristics actually get preserved in the rocks. But the point here I want to make is that these were formed under terrestrial conditions. There's fossil plant roots, and these are clearly terrestrial environments. Terrestrial, marine, land, water, land, water. Okay, over and over and over again. Okay, that's the big story here. Again, I won't go into detail, but just to give you an idea of, and again, you don't see these very often because they're on the prairie, because they're going to be covered over with grass. But you do see them in, cuts along streams and then road cuts. And these are all pictures taken from 177. Notice right here, and this is actually red, or the color didn't come through, this is pretty red here. And you saw this kind of rubbly looking stuff. Those are actually calcium carbonate nodules called caliche nodules. How many people have heard of caliche? Okay, some people. It's carbonate that forms within a soil in a fairly dry climate, kind of semi-arid kind of climate. If you go in some place, if you go to far western Kansas, you go down to New Mexico, the soils today would have lots of caliche nodules in them. In some places, the caliche nodules grow to such an extent that they create what's called hard pan, and it becomes completely useless agriculturally. So this is the same kind of thing, except we're finding it's 280 million years old, caliche. So this represents, so my point is you can learn something about climate from these rocks. This is 3 Mile limestone. This is one of the lowest of the chert or flint bearing limestones, which, and here I think you just about get to maybe on the shorter loop. And right below it, again, you won't see this in the prairie, but is this is called the Spicer Shale. This is the upper part of the Spicer Shale. It's kind of greenish or yellowish green in color. But if you see, you notice something weird here. See that? Wavy. That's actually a kind of a soil too. It's the kind of soil that you find on the U.S. Gulf Coast, Texas coast, for example. And it forms in a wet monsoonal climate. And it's a more clay-rich soil. And what happens is when it's wet, it expands. And when it dries, it shrinks. And so the soils are going every year, every season, expand, contract, expand, contract, expand, contract. And that pushes these soils into these hummocks. And they're actually preserving it. So again, this tells you that that's the kind of climate that was occurring at that time. All right. And I move on. This is just, this is again, right, this is the Florence, the big whopper thick one. This is the limestone, or the shale below it. one of the interesting things here, again, you can see this on 177, right about the middle, there's this couple horizons here that stand out, kind of red on the bottom, they get light colored on top. And if you zoom up on them, it looks like that. And these are actually burrows. And what they're burrows by is lungfish. And this represented a wet, dry climate where you have ephemeral or temporary lakes that dried up. And that's where the lungfish live. During dry season, they burrow down in the mud. They do what's called estivate, and they hibernate. And then when the rains come again, they come back out of their burrows, and they're happy. And so these were mostly fairly small lungfish, about as big as your finger. And lots of them packed in here. There's all these, looks like organ pipe. What's interesting is almost all those burrows have bone in them. This is one cool place we can actually find some vertebrate fossils. On 177, right before you get to the interchange with I-70.
Okay. Is it on the east side?
It's actually on both sides,
Both
but
sides?
it's better developed on the east side.
Okay.
And if you look at these, they weather out, they're filled with these little fragments of bone, these little kind of white flecks. What that means is lungfish didn't make it. So probably what happened is they burrowed down, dry season, and the wet season didn't come the next year. And they couldn't wait any longer, and they died. So it's really pretty amazing because these burrows are just, almost all the burrows have some fossil bone in them. All right. Now, basic picture here, right, is this alternation, terrestrial, marine, terrestrial, marine, terrestrial, marine, terrestrial, marine, terrestrial. What's going on, right? This happened dozens of times. Well, remember down here we have a continental glacier, right? And glaciers don't, or an ice age, just as an ice age. The time that the Flint Hills rocks were formed was an ice age. There wasn't any ice here, we were near the equator, we were 10 degrees north of the equator. Okay? But there was continental ice sheets down in the southern hemisphere. Down in the South Pole. So just as with the more recent Pleistocene ice ages don't occur by the ice kind of advancing and then nulling back, and that's the end of your ice age. What actually happens is it's pulsational. So the glaciers go like this when they're advancing, and then when they retreat, they do the same thing. So they advance a little bit and they melt back. They advance a little and they melt back. They advance a little and they melt back. Okay? And very complicated pattern. Now think what happens. Every time the ice advances, where does the water come from so that the ice can grow?
The ocean.
The ocean, right? So it happens, water evaporates from the ocean, comes, it falls as rain, it falls as snow, snow is converted to glacial ice, and it doesn't run back into the ocean again. You've interrupted the hydrologic cycle. So water is evaporated from the oceans, but it doesn't go back. So as a result, sea levels fall, right? Now, when the ice melts, what happens?
Sea levels rise.
Water runs back into the ocean and sea levels go up. So every time the ice advances, sea level falls. Every time the ice retreats, it goes up. So now the whole global ocean is going up and down like a yo-yo. At the time, we're a relatively low relief part of the continent. So when the sea levels were high, that water flooded in and covered us with a shallow sea. When the sea level was low, it drained out and it was all dry land. That's why you get this alternation. Okay? So the reason we're seeing these alternations is because these ice sheets in the southern hemisphere are going back and forth. Okay. I really am almost done now. So that's the Permian. What's really kind of interesting about the Konza is, Permian rocks, which are at the surface, basically. And then on top of those, you have, at least places, deposits of loose sediments, silts, sands, muds in some cases, mostly fine silts. Sitting on top of that were deposited during the last Pleistocene ice age, about 1.8 to 10,000 years ago. So you have a surface where you have 280 million year old rocks, essentially 280 million year time gap, and then Pleistocene sitting on top of that. And both types of rocks were both found in the two major ice ages of Earth history, just by kind of coincidence. So here's the Pleistocene ice age and Pleistocene ice sheets. This is a northern hemisphere glaciation. The Permian was the southern hemisphere glaciation. And this is the first extent. So here's the Kansan, it's the Illinoisan, right? Which poked into the north east corner of Kansas. And its furthest limit was just a little bit to the east of here, northeast of here. What you get is, well, two things. We get loess. This is a fancy name for glacial wind-blown silts. So what happens typically in a glacial environment, the edge of the glacier tends to be relatively dry climate, actually, cold, dry climate. And the glaciers are dumping enormous amounts of sediment at the end of the glaciers. And the wind is picking that up and carrying it away. And a lot of that got dumped here. And that's what you see here. So again, this is all Permian. And then 270 million year gap, and then this is Pleistocene. And this is all dumped in by wind during the last ice age. And it's in these sediments where people find mammoth teeth and ancient bison and deer and all those Pleistocene faunas, as well as Indian artifacts and everything. They're all in this stuff up here. So they might find them in the rivers, in the streams, but they're weathering out of this Pleistocene stuff that's sitting on top. This is in Wabaunsee County. This would have been near the edge of the glaciers. And what you find there on the tops of hills commonly are all these boulders and rocks, cobbles, but they're not of rocks that you'd find anywhere near here, even in Kansas. And they're actually quartzites, which are a metamorphic rock, a sandstone that's been placed under lots of temperature and pressure. And there's anything like it. And these are what are called erratics. These were carried down by the ice. And where were they carried from? Here's another one. It's called a subquartzite. You see these as building stones sometimes decorative stones. Someone just has one kind of sticking in their front yard. I think they look cool. But they look completely out of place, and that's the whole point. And this is where they're from.
I was going to say, I'm from Sioux Falls, and I recognize that.
Yeah, that's exactly where they came from. And this is all scoured over by glaciers. It has glacial striations and stuff. So the glaciers went over this area, scarfed up, picked up all this rock, ripped up all this rock, got mixed up in the ice, came all the way to Kansas, where the glaciers ended, melted back and dumped it all here. But it's actually from South Dakota. And then lastly, at the very, very top, to kind of connect with the earlier talk that we had near the beginning, is the evidence of the immigration of the first humans into North America, Paleo-Indians. And in Clovis culture, one of the first indications of the presence of humans in North America. So they're at the very top. Very near kind of as those last Pleistocene glaciers were retreating is when the immigration happened into North America. The very tops of those Pleistocene deposits is where you find the Indian artifacts. So, that's it.